It's enough. We waited 5 minutes. Someone else will join soon. So once again, welcome everyone to this new webinar. And in this new webinar, I will present a new element that we implemented in OpenSys, and that is mainly used to, as you've seen from the title of this webinar, to embed some geometry inside another. Okay, so typically to embed rebars inside solid domains, but it can actually be used also for other stuff. So just before we start, I want to specify that this new element is going to be inside the official OpenSys repository in the next days. So if you want to use it now, you need to download the OpenSys version from the Professor Petracca's website. Okay, that it is there in a beta version. So we are going to add it to OpenSys in the next couple of days. Okay, here we have someone else. Okay, so let me repeat this one for the new attendees. So hi everyone, for those who just joined. I'm going to present a new element that we added to OpenSys. It is called ASD Embedded Node Element. And as the name says, it is used to embed a node inside an element in such a way that that node can move together with the element. And it is typically used to create embedding, so to embed rebars inside solid domains, so to attach different geometries. And now I'm going to show you exactly how it works and how it can be used. So let me share my screen. Okay, can you all see my screen?
Yes.
Okay. Okay, so let me first show you where the new element is. Well, actually, it is an element inside OpenSys, but in STKO, it is a boundary condition. Why? Well, because what I wanted to achieve is to use a constraint that is able to attach to these joint geometries, not like an equal DOF or a rigid link, because they have some limitation. But I want to make sure that, for example, if a node falls inside an element, that node will move as the average motion of the element, which is not feasible, for example, with a rigid link, because the rigid link will make the entire element rigid, completely like a rigid body. Now, the problem is that in OpenSys, this kind of constraint cannot be added, because if you're familiar with OpenSys, constraints such as equal DOF or rigid links, they have typically one master node, so one retained node, and many constrained nodes. But in this kind of constraint, so if I want to say that the displacement of a node is the weighted average of the displacement of many other nodes, it means that I have only one constrained node and multiple retained nodes. And this is not possible in OpenSys. So that's why I decided to implement it as an element. Okay. But in STKO, you will find it under condition, constraints, multi-point constraint, ASD embedded node element. Okay, so this is the location, and now we'll explain. It has just 3 simple parameters, and I will explain what they mean. Okay, so now by tomorrow you will find a folder containing many subfolders. So some examples. How to use it is the first example that I'm going to show you. It's very simple, and with this kind of example, I will show you what every and single parameter in the constraint means. Then I will show you how to use this constraint. And here I will show you how to embed a bar inside a solid domain and to perform a pullout test, for example. Then I will use the same constraint for another purpose, which is, for example, to tie together 2 geometries that have incompatible meshes. For example, if you want to make a local refinement and you have a mesh that is much denser than the surrounding mesh, you can create two separated bodies, and you can attach them with this link. And then something a little bit more complicated, I will show you an example of a prestressed beam. Okay, so I will draw the beam as a solid domain, and then a cable inside, and that cable will be attached to the beam using this constraint. Then I will do the same for a reinforced concrete detail of a beam column joint. I will start with a linear model, and then I will show you how to change it into a nonlinear model. And then I will apply the same to a simple steel connection. Okay, so this kind of constraint has multiple usages, and it is very convenient, very, very easy to use. Okay, so now I can start with the first example. And the first example is how to use it. And the name inside is called pullout. Okay, now this is very simple. I will start from the beginning to show how it works. Okay, so now we have a simple, this one is a 2D analysis, and then I will show you the three-dimensional analysis, but the concepts are the same. I have two separated geometries. Okay, so a concrete body here and a beam, a rebar here. The two geometries are separated, so I need an interaction to connect them. I will explain you how to create this interaction, and then I simply need to create the physical property for concrete, the physical property for the beam, and then a constraint. And this constraint will join the beam inside the solid domain, even if their meshes are not compatible. If you see, and let's say if I hide the interaction, you can see that the geometry are separated. In fact, there is not a cut here. Okay, so it's simple a face and an overlapping beam. Okay, so they are separated. So typically these two geometries will move separately. Okay, and you can also see this feature by the mesh. As you can see, the mesh of the beam is not attached, does not have any common node with the solid body. Okay, and if you want to connect this node, for example, if I want to say that, let me do a drawing here. What I want to say with this constraint is that, for example, this node should move as a weighted average of the displacement of these other nodes, okay? Where the weight is the normalized distance from the nodes, okay? So for example, if I have a node here, it will move exactly as this node. If I have a node here, it will move as the weighted average of the two. So 0.5 this one plus 0.5 this one. If it is here on 1/3, it will move as 2/3 the displacement of this one plus 1/3 the other. Okay, so it's a simple linear interpolation. If it is exactly in the middle, it will be 0.25, 0.25, 0.25, and 25. Okay, so pretty simple. I'm just enforcing the displacement of a node to be the weighted average of the displacement of the surrounding nodes. And this is very different from the rigid link, because in the rigid link, the concept is different. These four nodes are slaves, and this one is the master. So the entire body will move rigidly. While in my case, my mesh can move free, and the inside node will move as a weighted average of the other. So it will not add any stiffness to the surrounding element. Okay, so let me try to explain this a little bit more. And I want to start from a clean model. Okay, so we start from 0. I just have my properties here. Okay, so the first thing that you need to do is to draw your geometry. Okay, now in my case, I want to create, let's say, a square of this size. Then I create a line. As you can see, the line and the face does not have any geometry in common. Okay, so they're just two simple detached geometries. Okay, perfect. Now let's go to the mesh and make sure that the mesh is not compatible. This is my global seed. It is fine. I want to use this one as quadrilateral mesh. Okay, and then if I mesh it, you can see that I have one mesh for my solid body and one mesh for my beam. Perfect. Now let's go back to geometry. Let's apply some material. So this one will be concrete. So I can just drag and drop the concrete material. This one is a linear elastic. I don't want to focus on nonlinearity. I just want to focus on the constraint. So a linear elastic material for concrete, an elastic beam section for the bar. Okay, so the properties of a steel and a 20 millimeters diameter bar. And then I have the beam property here. So I select this bar here and I drag and drop the beam property. If we go in property, you can see the extrusion. Same thing for the element. Okay, so for the solid body, I have a standard quad element. And in this quad element, I use the same thickness as the bar. Okay, but this is not important. So plane stress, 20 millimeters of thickness. And this is my beam. So I select the edge and I drag and drop the beam element. It is a force beam column. Okay. Perfect. Now let's apply some boundary condition. I want to fix the bottom. So if you look, or here we have someone else joining. So if I want to fix the bottom, in this case it is a two-dimensional analysis. I want to fix both X and Y displacements. So I select the bottom node, the bottom edge, sorry, and I apply the constraint. I apply the constraint. Let me go to the condition so you can see it. Perfectly. Then I want to apply some sort of imposed displacement here on top. And I called it pull. As you can see, it is a load, it's a load SP, so prescribed nodal value. Now I want to apply it to this node, and I want to apply a 50 millimeters displacement in the vertical direction, in the Y direction, and I want to fix the X displacement and the rotation above the Z axis. Okay. Only in this node. Perfect. Then I have another condition which is called embedded. Now I want to remove it because I want to show you what happens in this kind of model when you do not join the two geometries together. Okay. Then here I have a simple recorder. I just need to record the displacement, nothing more. Then I apply the boundary conditions. Well, at this point I have only the fixity, and here I was using the embedded, but now I will remove it. So I start from a clean model. So I add the boundary condition here at the bottom, and then I add the imposed displacement here with a linear time series. And then I perform a simple static analysis of 10 steps. Okay, so nothing special here. Now, of course, in this kind of model, if I try to run the analysis, I will see that my beam will move 50 millimeters as a rigid body in the upward direction without affecting the concrete body, because of course they are separated. Okay, so let's just verify this. Okay, let's go in the post processor. Perfect. So as you can see now, my entire body is fixed at 0, does not move, and the entire beam is moving at 50. Now let's change the color because here it is quite dark. Let's make it, for example, hot. Okay, so 0 here and complete rigid body displacement here. So if I try to do an animation, okay, you can see that my bar is moving freely because of course it is not constrained to the solid body. Okay, let's add this constraint now. So let's go back here and let's say I want to embed this beam inside the solid domain without creating any cut inside the geometry, okay? Because it is very annoying. Now in this case, the model is quite simple, but imagine if you have a very complex model and you have many rebars, you cannot think about cutting the solid domain in the same axis of each and every rebar that you have. It's going to take a lot of time. So what can you do here? The first thing that you have to do for using the embedded constraint is to create an interaction. Okay, you can give it a name. I call it embed. Then it is very important that you choose node to element links. Okay, why? Because in my case, the master geometry, so the retained geometry, is an element. Okay, so all the nodes of an element are retained, while the constraint node comes from the edge. Okay, so it is very important that you use node to element. Okay, then I press OK. I need to select the master. The master will be the solid body, so the surrounding material. And this is my master, right click. And then I need to select the slave geometries, so the geometries that will be constrained to move inside the solid domain, which is my edge now. Okay, right click. Now, as you can see in the geometry, you just see a bunch of dots here, so you do not understand what's going on actually. But if you go in the mesh and you mesh it, you will see that now every element is linked to the nearest, each and every node of the slave geometry is connected to the nearest element, okay? So for example, this node falls inside this element and it is connected to the entire element. Same thing for this node is connected with this element, okay? All the nodes outside are connected to the nearest element, which is this one, but then my constraint will ignore it, okay? So this is just the interaction. So the first step is to create this kind of interaction. Then you need to go in condition and you need to create a multi-point constraint. So you go here under condition and I call it embed. You go under model, constraints, multi-point constraint, and then you choose ASD, embedded node element. Okay, and you select the interaction. Now let me try to explain what these values are. Well, first there is an explanation here. Okay, so for example, the first penalty, the first value is K, is a stiffness value, and it is called penalty. Why? As you know, there are different ways to impose a constraint. One of them is the penalty approach. Now, for this kind of constraint, as I told you, in OpenSys, it is not possible to apply such kind of constraint. So I was forced to implement it as an element. And therefore, the only way to apply a constraint as an element is by using the penalty approach. Okay. Now, how do you choose this number? Here I said that the number should be large enough to enforce the constraint, but not too large, of course. Otherwise, the system will be conditioned, and I will show you. So, for example, if you choose a value of 0, it means there is no constraint. If you choose a value that approaches infinity, it will, in theory, enforce the constraint perfectly, but in practice, it will make your system singular. Okay, just because a number which is too large makes all the other numbers looks like 0, for example. So how do you choose this number? Well, I said you can estimate this number as, for example, the Young modulus of the material of the embedded domain multiplied by 1000, for example. So 3 or 4 order of magnitudes more than the Young modulus. Now, in my case, I have concrete, which is 30,000 megapascals. The thickness is 20, so I need to add another order of magnitude. So my entire stiffness, accounting also for the thickness of the solid, is 600,000. And then I use 3 order of magnitude more. Then I will show you what this is kind of an optimal value. Then I will show you what happens if you change this value. Then you have this flag here, ignore node outside. Well, the explanation is here, but basically you can, I would say you can leave it always checked, okay? Because in this case, if a node, for example, like this one, is outside the domain, it will not be attached to anything, okay? So only the nodes that are inside will be attached. If you does not click on this, so if you uncheck it, it will raise an error if some nodes are outside the domain, okay? Now in this case, I will have an error because it says, okay, this node, for example, is too far from the nearest element, is not inside the nearest element, okay? But typically you don't need it. It is just a check to make sure that all the elements are inside. So let's say leave it always as true, so checked. Then you have constraint rotation. Well, as I said, this kind of constraint by default constrains the displacement of the slave node to be the weighted average of the displacement of the master nodes, okay? But it does not apply any constraint to the rotation. You can choose it. So if you choose true, and this is valid, for example, if you have beams as slaves, because beams, they have both displacement and rotational degree of freedom, it will constrain also the rotational dot of the slave node to be equal to the skew symmetric part of the displacement gradient. So just to show you, just to recall a little bit of theory, you know that every matrix can be split. You can do an additive split of a matrix into a symmetric part and to a skew symmetric or anti-symmetric part, okay? Where, for example, a symmetric matrix, so you take the matrix A, and the symmetric part is equal to A plus A transpose divided by 2, and the skew symmetric is A minus A transpose divided by 2. Now, if A is this matrix here, A is the gradient of the displacement, so a matrix that contains the derivative of the displacement with respect to the spatial coordinate, this one will be called displacement gradient. And if you apply the additive split of symmetric and skew symmetric part, you exactly have the strain plus the infinitesimal rotation. In fact, the strain in a solid is computed as the symmetric part of the displacement gradient. The remaining is the rigid body rotation. And this is true in small displacement theory. In large displacement theory, you cannot use this kind of additive split. There is something called polar decomposition, but it is not the topic of today's webinar. So just to tell you that when you have a displacement field, you can compute the strain and the infinitesimal rotation. And this is what this constraint is doing. So if you check on this, the rotational dov of the slave node will be constrained to be equal to the skew symmetric part of the displacement gradient of the solid domain. But in general, you can keep it always true. So I typically always use these two values as they are. I just need to change the first number, okay? Because this first number is based on the physics that you are modeling, okay? So it depends on the Young modulus of the embedding domain. Perfect. So I do this, I have this new constraint, and of course I need to add it to the constraint pattern. So I go under multi-point constraint and I use embedded. Okay, now I can simply save it and run the analysis, and let's see what happens.
Massimo?
Yeah.
Can I ask you a question? So the skew symmetric part, the rotation is also the rotation of, like, so if you consider the face, it's the average rotation of the face of the four nodes, right?
Not actually, because in this case, the face does not have rotational freedom, rotational degrees of freedom. But actually, you can compute the rotation from a displacement field.
Yeah, so the rigid body rotation of the plane,
rotation, right? Exactly. Interpolated at the point it falls into. Okay, so for example, if it falls, this is the same thing. So let me do this drawing again. Now imagine I have a triangle here. So this is my body. And I have a node here, which is exactly on the centroid, okay? Now the displacement of this node, and let's call this one U1, U2, and U3. And this one is called U slave. Now it is, if it is, for example, in the centroid, then U slave will be equal to U1 divided by 3 plus U2 divided by 3 plus U3 divided by 3, because it is in the middle, okay? Now imagine, for example, if this node is not here, and the same thing for rotation, okay? So if I am here, I compute this, the rigid body rotation in this point, okay? Well, actually, for the rigid body rotation, it is the same, so because it is constant over the element. Now, if I move this point here, for example, in the middle of the edge, okay, now US will not have any dependence on U3, okay, because it is on this edge. So the distance from this one is exactly equal to 1, so this one goes out. And it will be U1 divided by 2 plus U2 divided by 2. So it's the weighted average of these two, okay? In the same way, if I move this node exactly on one of the three nodes, for example, in this case, U1, so also U2 goes out, and U slave would be exactly equal to U1. And in this case, basically, you recover an equal dov.
Okay.
Is it clear? And the same thing for rotation,
yeah.
okay?
Yeah,
the only difference is that rotation is the same thing, because the rigid body rotation is constant over the elements, okay?
Okay, okay, thank you.
Okay, so the analysis is done. I go back to the post processor, I reload it, And now you can see that my body is moving together with the beam, okay? And this is very convenient because as you have seen, you don't need to change the underlying geometry. You can simply apply this constraint and it will do everything by itself. We have someone else joining right now. Okay, so this is pretty convenient and very easy to use. Now, this example is pretty straightforward, but I will show you how to create much more complicated example, and it is as easy as doing this one. Okay, so the main topic of this kind of constraint is to embed something inside something else. Okay, so in this case, I embedded a bar inside a concrete domain. But actually, if you remember these concepts, let me do the drawing again. Where is the annotation? Disappeared. Here. Okay. As I said before to Dennis, for example, if a node falls inside, like in this case, here it is the weighted average of all the three nodes. But if another node falls in the middle of an edge, okay, it will be the weighted average of this edge. So for example, if my edge moves like this, so this node goes down, this node goes up, okay, like this, then my node will move here. So it will be forced to remain on the edge. And this is actually very useful, not only for embedding something, but also to attaching different meshes. For example, if I have a mesh here made of just two elements, and I have another mesh here which is much denser, like this, for example, I can apply this constraint, and this node will move on this edge. Same thing for this node, it will move on this edge, and all the others. So you can actually use it to do local refinement without propagating the mesh here. So it is very useful also to attach incompatible geometries. And it will make your modeling much faster. So let's see an example of using this constraint to tie together two incompatible meshes. So this one is the first example. I think it is pretty clear. If something is not clear, then we have time for questions. And this one is what you will see in the pullout test. Now let me save it, yes. And then I'm opening the second example, that is tie incompatible mesh, okay? And it is called tie model. Let me clear the output, it is already clear, perfect. So let's explain a little bit the geometry here. I have two separated geometries, okay? One is the surrounding faces. They will have a very coarse mesh. And then for some reason, I need to focus on what's going on here. Now imagine a soil, okay? And here you have your structure. And you want to make a good prediction only in this part of the soil, not in this part. So for example, here you can use a much denser mesh like this one. And here on the outside, you can use a very coarse mesh. What's the problem is that if you don't have any constraint, these two bodies will be separated. But if you attach them together, you cannot have this kind of mesh. You will have a kind of transition. So you will waste a lot of time because you have extra elements that you don't need. Okay? Now with this kind of approach, instead, it is pretty easy. You can draw your geometry outside, then the geometry inside. Then let me just move this one. I will show you how it works. Then you create an embedding, and actually I'm going to remove it and I want to create it again. So let's say I want to embed these borders to move exactly as these borders here. I do the same as I did before. Interaction. Embed. Just remember always node to element link for the embedding. Okay, so what is the master now? The master is the embedding solid, so the surrounding faces, okay, as I did before. Right click, and then the slave. The slave should be these edges because they are the only ones that I want to attach, okay? Right click, and now each one of them will be connected to the nearest point of the face. Once I've done this, I can move it back. Okay, so now you can see that every point of the edge is connected to the nearest point of the face. And if I do a mesh, I already prepared a mesh that has a global seed of 10 And here I used an edge seed, which is much denser, like 5 or 0.05, I don't remember the number, but which is much denser, okay? And now, as you can see, each and every node here on the border is connected to the nearest element. So this node will be connected to this element, okay? This node to the other elements, this node in the middle, and so on, okay? Now let's see what happens. Once you have the condition here, you just need to create an embed condition as you did before. Now let's see how I choose this number. Here I have, let me go in property. Okay, I have just one material, which is called concrete for both of them. This concrete has 30,000 as Young modulus. The element is a plane stress with a unit thickness. So how do I choose this value? As I did before, Young modulus of concrete, the thickness is 1, so just the Young modulus, 3 orders of magnitude more. And then I always choose constraint rotation, ignore node outside. Okay, this is not important because, for example, in this example here, I don't have any rotational freedom, but this is not a problem. If you have this check and you have rotational freedoms, it will be used. Otherwise, it will be ignored. And then, of course, I need to select the interaction to apply this constraint. So I have OK now. And if you see in condition, I have the fixity at the bottom, which is this one, fixity in both X and Y. Then I have an edge force on the top. So I want to apply a shear force in the horizontal direction. And I have my embedded condition on the interaction, okay? And then the analysis is pretty easy. A recorder, boundary conditions. So I use both the fixity here in the single point and the embedded in the multi-point. Then I add a load. The load is the edge force using a linear time series. And then the analysis, okay? Also here, the analysis is pretty simple. Nothing special. Okay, so let me run the analysis. And let's load the output, which is in time compatible mesh. Okay, now as you can see, let me increase a little bit the deformation. Okay, now as you can see, they move exactly together. And this is pretty nice because even if you have very incompatible meshes like this, they can still be attached. And the nice thing is that you can have a better stress resolution in the middle. So for example, if I look at the stresses, okay, and let me switch off the mesh edges. You can see that here inside you have a better resolution of stresses, while the outside, with respect to the outside. Okay, so this is pretty useful to have a local refinement when you don't want to deal with how to propagate the mesh, okay? Because it is very tedious to do this kind of refining. Instead, in this way, it is pretty easy, okay? Now I want to show you what happens if I don't choose the right number here. As I said, and it is also written here, this number should be large enough to enforce the constraint, but not too large, otherwise the system will be conditioned, okay? So let's try to play with it. Let's try to use a very large number, like 1 to the power of 20. Like this. Let's see what happens. Now, in this case, the number is very high, so I expect the constraint to be applied exactly. But the problem is that my system will be conditioned. Let's try to run the analysis and let's see what happens. You can see here, I have a huge error in the displacement norm, which is of the order of 1 to the power of 25 millimeters, okay? So it's clearly blowing away. And you may ask, why is this happening? Well, because if you have a matrix and you put a number there, which is extremely higher with respect to the others, all the others will be seen as 0, okay? Because they are much, much smaller than that number, okay? So the entire matrix will become a singular matrix, like a matrix full of zeros with this big number in the middle. So the number does not have to be extremely large. On the contrary, you cannot put a very small number. Now, of course, if I put 0, my system will be singular again because the edge, this portion here, will be completely disconnected. But let's put a very small number, like 1. So it is not singular, but it is extremely soft because it is 4 order of magnitudes less than the Young modulus here. So let's see what happens if I use such a small number. I can solve my system because it is not 0. But if I look at the results, okay, you will see that it moves, but it is not completely attached to the surrounding domain, okay? But as you can see, at least it moves, but it is not really attached, okay? That's why you can see compenetration and separation because the stiffness used here in this constraint is not enough, is very, very small. So let's try to see the range of meaningful values. Let's start from the Young modulus, 30,000, okay? And let's remove 1 order of magnitude. So this is 10 times less than the Young modulus. Reload it. It is pretty fine, okay? But if you zoom, you will see some kind of separation probably, or not too much. Here you can see there is a small compenetration, okay? It's not too much, but since it is 1 order of magnitude less than the Young modulus, there will be a compenetration that will be 1/10 of the entire displacement. So it can be enough. Let's reduce it of another order of magnitude. And now you will see a larger compenetration and separation. Now, whenever you see something like this, it means that your number is not chosen properly. Let's go down a little bit more. Now it is 3 order of magnitudes less. You can see an increasing compenetration and so on. Okay, so just to, and of course, then you will start having local stresses that are not realistic, okay? So the rule is it should be at least equal to the Young modulus, but I typically use the Young modulus with 3 or 4 order of magnitudes more. So I put the Young modulus here, which is 30,000, yeah, E3, okay? So I multiply it by 1,000, and this is pretty a reasonable number. Okay, so as you can see now, the stress distribution is very continuous, and you don't see all those overlapping. So this is the second usage of this kind of constraint. So you can either embed something inside something else, or you can attach to geometries. Okay. Now let's see some more interesting results.
Can I ask the question? So what happens if you use higher order elements like second order elements or?
You can do it. It's the same. Actually, we can do it right now. For example, you want to use higher order elements here in the middle or outside.
Yeah. So for example, inside second order elements.
Okay. Let's see. Okay. So first of all, I need to go. Let me remember what kind of second order elements I have in 2D. I think I have it, but probably they are plane strain. Well, that's not important. It's the same. Quad element, we have 9-node quad, which is a plane strain. So let me just change. Well, everything will be a plane strain, but I need to duplicate another one, and I call it LF4. So for example, here I go on quad. I use a standard quad for the outside, with a thickness of 1 and now plane strain. And I select the outside and I use the LF4. Then I select the inside and I use the LF9. Let me remove it. Let me rename it. So quadratic element for the inside. Okay, let me double check that the properties are different. Okay, they are different. Now, of course, I need to go into the mesh. And I need to say that this face in the middle is a structured mesh. with a quadrilateral shape and a quadratic order. Okay, quadratic, not serendipity, because quadratic makes 9 nodes, so also the node in the middle, while serendipity only makes 8 nodes. So full quadratic element on this domain. Assign, done, and rebuild the mesh. Okay, now you can see that the element is quadratic, also with the node here in the middle. Okay, the elements are assigned. Let me save it and run it. Of course, it is a little bit more expensive because the quadratic element is much denser, but you can do it. Here it is. And let's see it in the nodes, so you are sure that it is a quadratic element, as you can see here. So the nodes are perfectly attached. So there is no difference, because actually my constraint is actually attaching a node to an element. So it doesn't care what kind of element it is, okay? Because the source is a node, and it doesn't care where this node belongs to. And of course, if you see the stresses, there will be, well, in this case, you have different stresses, because you have this element gives you a different output, but it is the same actually. This is the nice thing of OpenSea, is that every time you change an element, you obtain a result that has different names, so they will be separated. But yes, you can do it.
So, for example, if you have, so if the problem was reversed, you had quadratic elements and you were attaching nodes to that quadratic elements, then you will have 9 nodes, the average of 9 nodes, or you would
No, I do something different. In this case, so what you were saying is what happens if the quadratic element is the outside, so it's the master. No, yes. Actually, to make it simple, when I implemented it in OpenSea, I made 2 elements. One to embed a node inside a triangle, and actually it is only one element that takes care of everything, but you can attach a node to a triangle or a node to a tetrahedra, okay?
Okay.
Then you say, okay, but how can I attach this node to a quad if you didn't implement it? Well, it's not a problem. What I do is I take this node, for example. It falls inside this element. Then I split this element into 2 triangles and I see what is the nearest triangle, okay? And then I do the same for every other geometry. For example, for an hexahedron, I temporarily split it into 5 tetrahedra, and I see what is the tetrahedra that embeds that node, and I use that part, okay?
Okay, I see.
Don't worry about it. You can use it for every kind of mesh. Then the Python script behind the scenes tries to create a subset of that higher order element, okay, to create the embedding.
Okay, I see. Thank you.
Okay, you're welcome. Okay, so now you have pretty clear how it works and what are the usage types that you can use. For example, embedding something or attaching something. Now let's see some more practical example. And for this practical example, I'm not going to model it over and over again because the concept is the same. You take the embedding domain, you take the embedded domain, and you create an interaction and you assign embedded. The embedded constraint should have a stiffness which is equal to the Young modulus of the surrounding domain with some order of magnitudes more, 2 or 3. So now let's open some more interesting examples. One of them is, for example, a prestress. So what happens if you want to model a prestress beam by explicitly drawing the cable, okay? Let me go here, and you can open this prestress model. Now let's see how it is done. Well, I have 2 models just because in this example I wanted to show you also something else, but they are 2 copies of the same model. So let's only focus on this one. You have one face, which is my beam here, and then I created a spline, which is this curved cable, okay? And you can create a spline like this, okay? So you can give it to whatever shape you want. So pretty simple, I created as a 2D beam here for the concrete, and this one will be the embedding domain. And then I have my cable, which will be the embedded domain, okay? And then as I did before, I create an embedded interaction. So, and I select the surfaces as masters and the beams as slaves. And just remember always to use node to element. Then actually here I have a linear time series, but I don't need it. Then I create an elastic material for concrete. Once again, I'm not interested into non-linearity here. Concrete for these two phases. Let's double check it, select, and you have the two phases selected. Then I want to create a material model for the tendon here. And since I want to apply prestress, I'm going to create a fiber cross section with a prestressed material. So how can I do it? Let me go in property. If you have never used the prestress, or if you have never modeled prestressed concrete, you can do it like this. So you first create a material for the steel. Now, in my case, it is elastic, but here you can use any kind of material. So either elastic or inelastic. So this one will be the base material. And of course, if you test it, it will start from 0. So for example, if I push it up to 0.1, oops, in monotonic loading, I just want to show you monotonic loading. Okay, this is linear elastic. That's perfect. And it starts from 0. What happens if I want to apply a pre-stress? So for example, I want to apply initial stress of 100 megapascal to the steel material. And then I do the same thing I did before. So monotonic and 100 subdivision to 0.01. You can see that now it doesn't start at 0. It doesn't start from 0, but it starts from 100, which is the initial stress. Okay. So this is typically used to take any kind of material and apply an initial state of stress. Okay, then once you're done with transforming your material into a pre-stressed material, you can create a fiber cross section. Now, in my case, it is a simple circular cross section, and here I use the steel pre-stressed. Okay. Once you have the fiber section, you create the section property as usual. Okay. Then I have two finite elements: the quad element for the concrete body, and the displacement beam column element for the tendons here. Then let's see the boundary condition. I have, let me go in condition. I have a pin on the left-hand side here, and I have a roller on the other side here. And then, of course, I use the embed. Okay. Once again, Young modulus times 3 order of magnitudes. Here, constraint rotation or not is not going to change the result. Okay, so once you're done with it, you can run your analysis, but actually here I made some extra script to do something, and then I will explain you. Now let's skip this one for a while. I want to show you how this constraint looks like when you mesh it. Okay, so you are here, you choose a global seed of whatever, I don't remember, it was 10. Then you mesh it, and now you can see that each and every node is connected to the nearest element. Here it is much more visible because the cable is curved, so you can see how each element is connected to the nearest embedding domain. Okay, this is pretty clear. It is very convenient because you don't have to go in each and every part and cut the geometry, so you can have a clean mesh, but you can still embed some geometries that do not follow that mesh. Okay, so this is the mesh. Let's go back to the analysis settings. So what I want to do here is to show also how to use pre-stress. Okay, now the problem with pre-stress, as you can see here, I don't have any load. I only have the pre-stress load. Okay, so I only have pin condition on one side, roller on the other side, but no extra load. My only load that I want to analyze is the load due to the pre-stress. Now, when you do an analysis like this, so I apply a recorder here, then I apply boundary conditions, which are pin roller as single point constraint and embed as multi-point constraint. And then I do an analysis of 10 steps. Okay. Now, what would you expect in these 10 steps? Well, since the press stress is given directly inside the element, or actually inside the material, in a single step, this beam here will shrink, or will actually bend to apply the press stress. The problem is that this happens in one shot, so it happens instantaneously. This is fine because typically the press stress load is not so high so that it breaks the concrete, okay? But sometimes you may have so many nonlinearities that you would like to apply press stress into an incremental fashion. This is one reason. Another reason could be, for example, if you're doing dynamic analysis. So applying the press stress in a single shot can create some oscillations, while you can apply it, you would like to apply it in an incremental fashion. So how can you do this? Here I created a small script to update the parameter of the initial stress only on the top beam so that you can see the difference. So the bottom beam here uses directly the pre-stressed material. And here I created a parameter and a custom operation to update that parameter. And it is assigned only to the top beam here, okay? So for example, how can you create a parameter? Well, the first thing that you can do is to create a selection set with the tendon on the, with only this one. So if I select this one, you can see that my selection set points only to the model on the upper side. Then you declare a parameter. Now the parameter name depends on the material that you're using, but in this case, for the, what is it, the initial stress material, the parameter is sigma 0. Now you may ask, how do I know what kind of string I have to put here? Well, you need the source code of OpenSys, because unfortunately the parameters that you can upload, that you can update are not explained into the documentation. So if you're not familiar with OpenSys, I can show you how to go and look for the parameters that you can update. Now in my case, for example, let's say I don't know anything about the initial stress material. Well, the first thing that I need to do is to go and find where is the initial stress material inside my source code, okay? So let's try to write something like here, initial stress, and I will not find anything, because if I recall correctly, it is called init stress material, or just init stress. No, init stress material, yeah, that's fine. It is this one under uniaxial material. So init stress material dot cpp. And as you can see, he found a file called init stress material under uniaxial material. If I open this one, this is a standard OpenSys material. And if I navigate to init stress, and then I look for the set parameter command, I click here and it goes down to the set parameter. And here I can see all the parameters that I can update. Well, there is only one parameter that I can update, and it is called either sig0 or f0, or f0 with the capital F. Okay, and this is the way you understand what kind of parameter you can update into a material, unless it is documented. Unfortunately, it is not documented, this one. So sig0 is fine. So you first declare a parameter. A parameter is called, it is under model, misc command, where is it? Parameter, okay? For the parameter, you have to choose a selection set for which this parameter that will be affected by this parameter, okay? So in my case, I want to affect only the beam elements on the top model. So I use the selection set of the tendon one. Then you can choose if it is an element-based or a node-based parameter. Now, in this case, it is an element, because I want to change the parameter of a material, and a material is inside an element, not inside a node. So I choose element. I don't care about random variable. This is for another usage. And then there is specific object argument. So the name of the parameter that you want to update. Now, in my case, the name is sig0, okay? Then I create a custom operation to update the parameter at each step. I already talked about custom operation in some of the previous webinars. So everything you need to do is to create a simple Tcl function. For example, in my case, it is called update sigma 0. I want a reference initial stress of 100. I know that my time increment is 0.1. So I create a function that takes the current time. If the current time is less than 1, I update sigma 0. So I take my new sigma 0 to be equal to the reference value times the current time. But the current time in a static analysis goes from 0 to 1. So it's like a percentage. So when I am at the start, it will apply a 0 initial stress. When I am at the end, it will apply the total reference initial stress. Okay, so once I've created this procedure, I can append this procedure to all my custom functions. Now, this one is something that STKO creates automatically, and all the functions that are put inside here, they will be called after each stage of the analysis, okay? Actually, after each step. So for example, here to show you what is going on, I also print something. So you will see now that at the end of each step, you will see a print here that says T is equal to the current time. And so my sigma 0 is equal to this number. And let's see what it is. So this is the only thing you need to do for updating a parameter during the analysis. Now, if I run my analysis, let's see what happens. Here you can see that it does, for example, 2 iterations for the first step, and then it prints T is equal to 0.1, sigma 0 is equal to 20. It's not equal to 10 but 20, because since it is done at the end of the step, I need to apply also the step increment of the next one. So at the end of this, I will have 20. So the starting point for the second step, which is the 20%. Then I have 30 because I have 30 here, and so on. And just before starting the last step, I have 100%, and then I perform the last step, okay? So let's see the output of this one. I go to prestressed. I load the result. Now at the end, the result is exactly the same. Let me increase it a little bit, okay? But if you do an animation, you will see that this one is already started directly from this deform configuration. Why? Because at the first stage, the entire prestress is applied. So it suddenly goes from the initial position to the final deform configuration. And this one can give a shock if you have if you're doing a dynamic analysis, or if you have a lot of nonlinearities. This sudden load can create some problems, some convergence problems. Now, not in this case because it was elastic. But here instead, I use the update parameter, and you can see that my beam is loading, is actually applying the prestress one step at a time. So this is kind of an extra. I wanted to talk about the embedding, but you also learned how to use the parameter to update your model. Okay? So, now we'll show you other 2 examples, but very fast because we're almost out of time, and then we will have time for questions. Now, the other 2 examples can be a little bit more interesting. I'm going to the 3D models. I'm going to save this one. And then I have 2 kinds of 3D models. Now, I'm not going to explain too much because you already know the theory now. Reinforced concrete, and here you will find a nonlinear version of this one, but it is the same. So if you want to do a detailed analysis of a concrete member, like in this case, it is a detailed of a beam column joint, it is pretty easy. You just need to create, for example, a solid domain. Let me go in property. Yeah, here, and I want to switch off the nodes. Okay. So I have a property, but physical property. Perfect. Let me switch off the grid. Okay, so you can see that it is quite interesting. What I want to do is to, for example, if I select this one, which is the concrete domain, and I show only this, you can see that the solid domain is pretty simple. They are just 4 solids, okay? Nothing complicated. There is no cut to place inside the rebars. So there is nothing special. It's a very simple solid domain. Now, if I select this one and I hide it, and I also select the embed condition and I hide it, you can see what's inside. Okay, here I model a series of beams. They are actually just lines, okay, with a beam property that gives the exclusion when you are in properties here. So I created 4 or 5 groups. One is vertical rebars, okay. Then I have 2 groups for the column stirrups, the stirrups column 1, the outer stirrup, okay, and the inner one, select. And as you can see, you're free to create stirrups with chamfers. They can be overlapping or they can have a real offset. It's not important because you are not going to do any cut in the solid geometry. And then the same thing for the beam. Here I have my horizontal rebars. You can create also the anchorage here. So you can go into detail, into whatever kind of detail you want, okay? And also the stirrups for the beam, okay? So as you can see there, you can model whatever you want inside, but the solid domain, the outside solid domain is extremely simple. So you don't need to do any cut here. As I said before, the only thing that you need to do is to create an embed interaction, which is a node to element. In this case, the solid domain will be the master, so the entire solid domain, and all the edges of my vertical fibers, stirrups, horizontal fibers, and so on, they will be the slaves. Okay, so you create just one single interaction here and you're done. Well, of course, once again, you have to create the embed condition, and also in this case, concrete, Young modulus, 3 orders of magnitudes more, and you constrain rotation. That's all. You set up your analysis. Now in this case, I decided to apply a rotation here on the beam side. And how do you apply a rotation on a solid face? Well, you can use a prescribed value using a function here. How does this function work? Well, you can go here in front. The z location of this point, as you can see, the z location of the middle of the beam is 1000. Okay, if I put myself here in the middle, you can see that it is 1000. So my function can be, for example, z coordinate minus 1000, so that here that would be 0, divided by 200, and 200 is the total height of my beam. And in this first part of the function will be a normalized butterfly shape. Okay, so it will be +1 here and linearly goes to -1 here. And then I multiply by the real value that I want. So here I want 10 millimeters, down I want -10 millimeters, and it will apply a rotation in terms of displacement. Okay, and then you just run the analysis. Now I have, actually this model is I made it quite fine, okay, but it is not actually necessary. So I prepared this model for parallel analysis, 6 processors. So in this case, you need to change the solver to OpenSys MP. It is already set up for running parallel analysis. And if you want to go and look at the result, you can go under RC detail and you load one of them. Okay, so this is my model. As you can see, the beams are still moving inside, but if you want to look what's going on inside, you can do, for example, a Gauss plot for my fibers, or for my concrete, sorry. I want to switch off mesh edges, and I want to visualize, for example, the material stress, let's say the shear stress in the XZ plane. Okay, so I have let me increase the particle size a little bit, like 5. Okay, so you can see the major shear stress here in the joint, and I can switch off the beam extrusion now, because then I can overlap, for example, a beam diagram plot, and here I can visualize the normal stress in my beams. So that it will be the stress in the fiber, stress in the rebars times the area. Let me make it a little bit smaller. Okay, And this is the nice thing. You can also visualize what's going on directly inside the rebars in terms of stresses. So it is pretty interesting. Okay, you can do a lot of things with this kind of modeling. Or just to make sure that they are all inside, I'm going to apply a deformation here so that you can see that the rebars are actually following the solid domain. So it is a very convenient and easy way to do this kind of detailed analysis without going crazy with the geometry. Okay, so this is pretty nice. And then I will show you a last examples. It is also very useful to do the detailed analysis of steel connections. No, I don't want to save it. I'm just going steel connection. Well, this one is the same, RC detail, and L stands for nonlinear. I just changed the linear model to nonlinear ones, and also the beams are now made with fibers, but the analysis is the same. We have something on the chat. Yes, without sleep. Let me see the first questions. Yeah, actually, we are almost done. Yeah, we are almost done. It is without sleep, but actually the sleep can be included very easily. And in fact, I will do it in the next couple of days and I will post it on the forum. It will be directly made inside the Python script. So it will be very easy to add it. And it will be a topic of the next, not actually the next webinar, the other one. But if you post this question on the forum by tomorrow, I will prepare a script that will be in the next version of STKO. So you will have also the sleep. So go here in steel connection. Also here, pretty simple. You have a geometry, for example, of your column here. Okay, of your column here. Then you have another geometry of your beam, but you don't want to create the cuts here to make sure that the beam is physically attached. Okay, so you create two separated geometries. Okay, like this one. If I want to hide this one, and I hide also the interaction, you can see that there is no cut here. Okay, they are perfectly separated. So you do that. Once again, you create an embedded condition. You assign an embedded boundary condition. Now this time it is the stiffness of the steel, 3 orders of magnitudes more. And you do your own mesh, and as you can see, the mesh, they are not compatible at all. But when you run the analysis, they will be attached. No, probably also 100 is fine. Oh, too much. Okay. And you can see that they are perfectly attached if you calibrate properly that number. So this is pretty convenient for doing all this kind of detailed analysis without going crazy with the geometry. Okay. So yes, we are done with today's topic. I hope you enjoyed this new element. It will give you a lot of new possibilities for doing this kind of detailed analysis that were very difficult to do before with OpenCS alone. So please, if you have any question, we have some time for questions.
Massimo, can I ask a question?
Yeah.
So, for example, so if I understand it right, so it's a flat tetrahedron element that that does this averaging during the factorization of the stiffness matrix, right?
Yeah, actually, it is not a tetrahedron element. It is I created an embedded condition. Well, actually, let me show you the source. How it creates the TCOL file. Just want to show you, but I have to share my screen. If I go inside the pullout test, which is the easiest one, and I go under analysis steps, when I create the embedded element has the constraint node tag first, and then it can have 3 or 4 retained nodes. Now, in my case, it is a 2D analysis, so it only has 3 nodes. They are physically oriented as the triangle. So STKO gives these three IDs as the IDs of a quadrilateral, for example. Let me show you. I mean, there is not a physical triangle there. Okay, I have my mesh element, which is, for example, this one. Then I have a node here, which is embedded into this surface. Then STKO takes this element, tries to find the two triangles that form this quadrilateral, and tests for the embedding of this node inside one or the other. Okay. Then, of course, only one triangle will contain that node, and I will take the three ID of these nodes and I will put it there. Okay. So this one is the node of the constraint node, and these three are the nodes of the nearest triangle. But it doesn't mean that a triangle should be there in OpenSys, okay? Just three nodes. The same thing for the tetrahedron. That's why I'm saying you don't need to actually do a mesh with triangles, because here I do not pass the tag of an element. I pass the tag of three nodes. So they can be the three nodes of a real triangle, or three nodes of a quadrilateral, or three nodes of a 9-node element, for example. Okay.
Okay. So what I wonder is, like, for example, when the OpenSys is running, when the OpenSys is calculating the stiffness matrix, it asks this element to return the stiffness at the start of each factorization process. Exactly, yes,
like any other element.
So I think, that means that, for example, if I use the linear algorithm, and if I use, let's say, factorized once, then this constraint will not work, or work. What do you think?
No, it will work. It will work the same, because the stiffness matrix of this one just depends linearly on the displacement. It doesn't change with the displacement. It's not nonlinear.
Okay.
Why do you think? Yeah, I mean, for example, if you look at the stiffness metric of this one, or let's assume you have a triangle. Let me clear this one. You have a triangle, and you have the node here in the middle, in the centroid. Okay, so your constraint is that, let's call it U constraint, and this one will be U1, U2, and U3. Your constraint to apply is that UC minus U1 divided by 3 plus U2 divided by 3 plus U3 divided by 3 is equal to 0. This one is your constraint. Now, how do I apply this constraint here? We've been talking about how to program finite elements using the standard B matrix. Okay. Now imagine this one is my element, an element made of 4 nodes. The first one is the constraint, and the other are the retained nodes. My constraint matrix here will be, imagine this one is like a deformation. Okay, so this one is a displacement jump, but for me it's like a deformation. Okay, so my B matrix will be something like 1, which corresponds to the first node. Then I have a bunch of zeros here. Then I have minus 1 over 3, minus 1 over 3, minus 1 over 3. Okay, and this one will give, actually on the same row, sorry. I have 1, minus 1 over 3, minus 1 over 3, minus 1 over 3. Okay, this one is my matrix that, multiplied by the displacement vector, UC, U1, and so on, it will give me this displacement jump, which is my epsilon. Okay,
I get it now. Yes.
So this one is my B matrix, and my stiffness matrix is B times K. In this case, K is the penalty parameter, times B. So this one is constant. Okay, as you can see here. Like any other finite element, I told you, any kind of element can be formulated in the same way. The only difference is that now here, instead of having a physical stiffness, you have a penalty.
Yes.
And the higher is this penalty, the more this epsilon goes to 0. So it means that actually this strain, because this strain is the jump between the constraint node and the retained nodes, and it should be 0 to be exactly. But if the stiffness, if this matrix is very small, they will be different, okay?
Yes, thank you. It's very clear. Thank you very much.
Is there any other question? Of course, you can also post questions on the forums if this is not clear enough. I know probably from the mathematical point of view, it's kind of tricky, but the usage is very simple, okay? So you identify what is the master, so the embedding domain. You identify what is the slave, so the embedded domain, and you create just one single interaction. Just remember two rules. The interaction should be node to element, and the stiffness penalty should be the Young modulus of the surrounding domain increased by a factor of 1000, for example, so 3 orders of magnitude, and it should be enough. Is it clear to everyone? If you have any question, we have other 5 minutes or more. And you will have all these materials by tomorrow on our website. Let me see. We have another question here. Would changing the triangular interpolation to some other geometry improve the accuracy of the simulation? Actually, yes, but it's not that much. I mean, to be clear, I needed to create many constraints in OpenSys, okay? So one that attaches a node to a triangle, one that attaches a node to a quadrilateral element, and so on, okay? Because, for example, when I said, let me do this check, let me do this. You were right, you got the point. Let me try to explain. Oh, I need to share the screen before drawing. Okay, so imagine that if you have a quadrilateral, for example, and I have a node here, well, in this case, using the full quadrilateral or the triangular subset does not change, because since I don't have any dependence of these two nodes, I only depend on these two, the displacement between them will be linear, and it is the same. If I am in the middle, there will be a difference, because a triangle can only represent linear displacement, while a quadrilateral can represent a bilinear displacement. So linear in this direction, but the cross product of them is not necessarily linear. So it can be like this, it can be like a paraboloid. So yes, it will be a little bit more accurate if you use different interpolation, but it takes a lot of code. So instead, how I did it, I needed to create just 2 elements in OpenSys, one for the triangular case and one for the tetrahedron case. In another case that you can see some sort of less accuracy is, for example, if you have a quadratic element, imagine like this, with a node here in the middle, okay? If this is a quadratic element and this node moves here, and this node, let's say, moves only here, you will see a quadratic displacement like this in reality, okay? Now imagine I had a node here. This node will be linked to move on this edge here. So the initial edge of a triangle, of a fake triangle. So my node will move actually on the chord between this node and the other, okay? But this is actually not so much visible, because if you're really interested in this curvature here, it means that your element is too large, because the finite element typically should be small. So this distance is not that much. But yes, there can be some differences, but don't worry about them, because I made all the tests, and using the triangular or the tetrahedral interpolation is more than enough. Probably in the future, I will implement it also for the others, but for now it is enough. But yes, good question. Is there any other question? Okay, so if there is no other question, thank you again for taking part to this webinar. Hope you enjoyed it. And by tomorrow, you will see, oh, thank you, Sauja. And by tomorrow, you will have access to all this material that we use today. Just remember, for the ones that connected late, this element will be in OpenSeas very soon, in the next couple of days. But if you want to use it right away, you need to download OpenSeas from Professor Tarke's website, because his own version of OpenSeas already contains this element, okay? Okay, so once again, thank you everyone, and hope to see you on the next webinar. Bye everyone.